Now, in the previous lecture we have given a brief introduction on the iteration methods for solving the system of equations Ax is equal to b. Let us just define what we have explained last time. We have defined the iteration methods. We have again the system of linear system of algebraic equations Ax is equal to b. Then we want to write an iteration method which iterates a given estimate, that is an initial approximation, and then iterates further and further. That means we would like to write down an iterative procedure of the form xk plus 1 is h xk plus some c, where h contains the component of a, and we call this h as the iteration matrix. The reason being the convergence or divergence of the iteration method would depend on the properties of this matrix, and hence it is called the iteration matrix. And we have also given the C as the one that the contribution of B is in C. Now, the first method that we would like to describe in this is called the Jacobi iteration method. We call this as the Jacobi iteration method. This method is a very straightforward and simple method. In all iteration methods we solve the equations one by one. So, we iterate it first equation, then we solve for the second equation, for third equation, and so on. So, this is how an iteration procedure goes on. So, let us take the first equation in this set. The first equation reads a11 x1 plus a12 x2 a13 x3 plus so on a1 n xn is equal to b1. This is our first equation. The method proposes that we take all the variables x2 x3 xn to the right hand side, keep the first variable from the first equation on the left hand side, then take the iterate on the right hand side as of the previous iterate, and the one on the left as the current iterate. That means I would write this as x1 is equal to 1 upon a11. I have taken everything to the right hand side and divided by the pivot. So, that will be b1 minus a12 x2 plus a13 x3 plus so on a1 n xn. Now, once you take this to the right hand side and write in this form, I would now define a new iteration as, now you can put this superfix k plus 1 here, put k over here, put k over here, and k over here. That means all these values on the right hand side we are using at the previous iterate, and we are now obtaining the current iterate x1 at k plus 1. Similarly, the second equation we shall retain the second unknown on the left hand side and take all the other variables to the right hand side. That means I would like to write down x2 k plus 1 is equal to 1 over a22, that is the pivot a22, and that is b2 minus a11 x1 k plus a21 a23 x3 k plus so on a2n xn at k. So, we are taking a21 x1, a23 x3, a2n xn to the right hand side, and all of them shall be evaluated, all of them are evaluated at the previous iterate k, and we obtain the present iterate x2 k plus 1 from here. So, in general therefore, we have, I can write down any ith variable. If I take the current iterate is a plus 1 upon a I, the right hand side is bi minus all the values up to xi, that means a I1 x1 of k plus so on a I minus 1, that is the previous one to this, that is xi minus 1 of k, then this particular value is missed. Therefore, I will have the next one as I plus 1 xi plus 1 of k plus all the remaining values a I n x n of k. So, this is the value corresponding to x I is missed here. So, a I term is missed here, and we have the all the other variables on the left of x I and on the right of x I brought to the right hand side and written in this particular form. If you write down the entire system in this particular fashion, I is equal to 1 2 3 n, if you write, all of them are simultaneously being displaced on the right hand side by the previous estimate, the previous value. Therefore, sometimes the Jacobi iteration method is also called method of simultaneous displacements. So, we are defining them replacing the right hand side simultaneously, therefore, it is called method of simultaneous displacements, because some books do use this word simultaneous displacement in place of the Jacobi iteration method. Now, an important thing to note here is that the system, these equations are being solved, first equation for first variable, second equation for second variable, and so on, nth equation for nth variable. Therefore, the convergence property of this would depend on the order in which you are solving. If you interchange an equation, the properties are going to change. Therefore, it is very important that we retain the equations as given in that particular one, unless we have a specific reason that your pivot is become 0, or you want to improve convergence by theoretically showing that if I interchange the equation in this particular fashion, I get better convergence. So, I can interchange the equations, otherwise the given equations as given shall be used. The procedure which I adopted can be used for actual computation purposes, but if you want to analyze it, the methods we would like to have the matrix notation for this Jacobi iteration method. So, what we let us call it as matrix notations. The coefficient matrix A, given this coefficient matrix here, I will write it into sum of 3 parts. The diagonal part, the diagonal matrix I will call it as D, the strictly lower triangular part I will call as L, this I will call it as U. That means, I would like to write down A is equal to L plus D plus U. For example, let us take say a matrix 1 2 3 4 4 5 6 7 2 minus 2 2 0 2 0 1 2 3 6, or let us change it 1 4 3 6. Now, if this is the matrix given to us A, then I am defining L as the strictly lower triangular part. That means, everything will be 0 here, this, and this strictly lower triangular part is 4 2 minus 1 1 4 3. So, this is the diagonal and above is removed, and whatever is strictly lower triangular I will call this as L, that is the strictly triangular lower part. Now, D is simply the diagonal part of the matrix. So, it will be simply 1 5 2 6. So, this will be the diagonal matrix, diagonal part 1 5 2 6, and U is the remaining part, the upper triangular part. So, here we will have all zeros in the lower triangular part including the diagonal, and this part is 2 3 4 6 7, and of course, here it also 0. So, I will have a 0 over here. This is the breakup I would like to take for the given matrix as strictly lower triangular part, the diagonal part, and strictly upper triangular part. Now, if I write it this way, then the system of equations can be written as A x is equal to B. So, I can write this as L plus D plus U of x is equal to B. Now, if you just look back at this particular way in which we had written it, you can see that these are all division by pivots, A11 here, A22 here, AI here. that means these pivots are coming from the diagonal elements. Therefore, I would keep d on this left hand side and take the remaining things to the right hand side minus L plus u of x plus b. So, I take this contribution of the lower triangular part and the upper triangular part to the right hand side and write it as dx on the left hand side. Now, the iteration reads d of x k plus 1 is minus L plus u of x k plus b plus b. Now, I take d to the right hand side, invert d. So, I will write this as d plus 1 x k plus 1 is minus d inverse of L plus u x k plus d inverse of b. This is our h x k plus c which we had written earlier. Therefore, h is minus d inverse L plus u. This is our iteration matrix. This is our iteration matrix and C is d inverse of b. Now, we can see that here we are using d inverse. D is a diagonal matrix, therefore, its inverse simply will be 1 upon a11, 1 upon a22 and so on. Therefore, in this case d inverse would be simply 1, 1 by 5, 1 by 2, 1 by 6. So, in this case, in this example we will have simply d inverse as 1, 1 by 5, 1 by 2, 1 by 6. So, that is how the when we had written this method for simultaneous displacements here, you can see this again, this is d inverse, the component corresponding to the first one, or 1 upon a11, 1 upon a22, 1 upon aii. Therefore, that division is coming from the multiplication by d inverse. Therefore, this iteration matrix will play the complete part in the whether this method is going to converge or it is going to diverge. And of course, in the limit we would expect that this will go to x is equal to a inverse b. However, when if the numbers in your system is very large, then we may expect lot of round off errors in the procedure. Now, we can write down a very interesting alternative way of writing this method for computational purposes, wherein we would like to tackle numbers which become smaller and smaller. Here suppose the solution is minus 10, the other is 15, other is 50, like that. So, that those solutions are going to come from the Jacobi iteration, but we will modify this and write an alternative method, alternative way of doing it, which allows us to work with smaller and smaller numbers. That means, we will tackle the errors and not the solutions. Now, what we do is we just make a simple manipulation from this procedure. So, let us start with this. Let us start with the x k plus 1 is equal to minus d inverse L plus u x k plus d inverse of b. So, I am starting with the method that is given over here. What I do here is I add and subtract x k. I add x k here and subtract x k. Whatever I have subtracted x k, I will combine with this x k. So, I will insert it inside as I into x k plus d inverse L plus u of x k plus d inverse of b. So, I have added x k and subtracted x k. So, this minus x k I have included in this one. Now, I will make a small manipulation here. I will take d inverse outside. So, I will be d into d inverse. So, d inverse. So, I will write down d inverse of d L plus u. D inverse I have brought it on the left multiplication factor. So, I will have this as x k plus 1 x k and d inverse of b. But by definition d plus L plus u is a. So, I bring back a here. So, this I will write it as x k minus d inverse of a x k plus d inverse of b. Now, I bring x k to the left hand side. So, I will write down x k plus 1 minus x k is equal to d inverse b minus a x k. I have combined these two, I have taken d inverse out. So, b minus a x k. Now, you can see this is a very interesting equation. The left hand side is the difference between the two estimates. If it is converging, this is going to be 0. Therefore, this is nothing but our error of approximation. This is error of approximation. If you look at this right hand side, this particular part, this is how well the system has been, equations have been satisfied. This is a x minus b or b minus a x. Our system of equations is a x is equal to b. Now, this shows how well the equations given in system is satisfied. So, this gives you the error in satisfying the given equations, error in satisfying the given system. A x is equal to b. Now, this we shall call this is called as a residual of the system. So, we call this as residual vector. We shall call this as residual vector and give a notation to it as vector r k. This is a vector r of k, and this is error approximation. This we shall denote it by some v k, we will denote it by v k. Therefore, I can write this system as v k is also a vector, of course, these are all vector, that is equal to d inverse of r k. Or if I want to write d on the left hand side, I could as well write d of v k is equal to r k. Now, I would prefer this particular system to be solved computationally, because as the convergence is achieved, x k plus 1 tends to x k, this x k plus 1 tends to x k, and a x k also tends to b. That means, v k tends to 0 and r k also both tend to 0. Therefore, as convergence is obtained, v k tends to 0, r k tends to 0. Therefore, we are computing with smaller and smaller numbers. Therefore, the amount of round off error also would go on reducing. Therefore, in this way we will be controlling the round offers completely. We are not saying for a trivial problem of 10 by 10 or 15 by 15, we are talking of thousands of equations, wherein you will have to use it so many times and this, so that the round off error can affect few places of your solution. In this case, the solution would not be affected, because the much less round off error than what it would be in the other case of the problem. Now, this is called a Jacobi iteration method. This was one of the first methods that were discovered for the solution. There is an obvious disadvantage in this particular method as we have done, and the disadvantage is, we know we are solving equation by equation. If I solve the first equation, I have now found out x 1 k plus 1, but when I went to the next equation x 2 k plus 1, even though the solution x 1 k plus 1 is available to me, I am not using it here, I am using only x 1 k of this one. And when I come to the last equation, for example, when I come to the last equation x n, I have already computed x 1, x 2, x n minus 1, but none of these informations are being used in computing the present iterate. We are still using all the previous iterate, and hence the convergence will be slow. And if I now include that at every stage information, if I am solving the ith equation, I minus 1 variables have already been solved. So, therefore, that information can be used now to get a better estimate, and if I do that, it is called the Gauss-Seidel iteration methods, and it turns out to be one of the most powerful methods even today. So, that is called the Gauss-Seidel iteration method. Gauss-Seidel iteration method. So, let us straight away write down, since we have just explained, therefore, we will have x 1 k plus 1 will be the same equation as we have in the Jacobi. So, the first equation remains the same, b 1 minus a 2 1 x 1 x 2 of k plus a 2 a 1 2 of this a 1 3 x 3 of k plus so on a 1 n x n of k. Now, we write x 2 k plus 1 upon a 2 2 b 2. Now, I have x 1 k plus 1 available to me, therefore, I will now use that current estimate of x 1 k plus 1. A 2 3 I do not have x 3 as it. So, I will use the previous estimate only and write down a 2 n x n k. Like that, then finally, x n k plus 1 will be 1 upon a n n b n. Now, all the previous values have been computed. So, I will have all of them from the previous x n minus 1 of k plus 1. Now, when we have reached this last equation, all the previous variables solution has been obtained, and hence I use the whatever current available values that shall be used on the right hand side to produce this particular this one. This is called the Gauss-Seidel iteration method. We shall show later on that theoretically we can prove, if A is symmetric matrix for example, or in general in the general case also, that Gauss-Seidel is at least 2 times faster than the Jacobi iteration. I mean, rate of convergence we are talking, it is actual computer time you can also count upon it. It is at least 2 times faster than the Gauss-Jacobi iteration method. Now, for analyzing it for the convergence analysis, I would like to write down in the matrix format. What I would do is, I will have to retain all the current iterates on the left hand side. So, I will bring everything to the left hand side and write this equation. So, let us rewrite this equation, first equation. This is a 1 1 x 1 k plus 1, a 1 1 x k plus 1, and the let us leave some space here. So, that is visibility I can leave it. So, this will be equal to b 1 minus a 1 2 x 2 k plus a 1 n x n k. So, I am cross multiplying it and taking if there is a current iterate, I will take the left hand side, here there is nothing. Now, you can see if I go to the next equation now, if I take the second equation, this is a 2 2 x k plus 1 and this is also the current iterate. So, I will bring it to the left hand side. So, I will write this as a 2 1 x 1 k plus 1 plus a 2 2 x 2 k plus 1, and the right hand side is b 2 a 2 3 x 3 k plus a 2 n x n k. Now, if I go to the last equation, I am multiplying this, all of them belong to the current iterate. So, all of them come to the left hand side. So, I will have here a n 1 x 1 k plus 1, a n 2 x 2 k plus 1 plus so on a n n minus 1 x n minus 1 k plus 1 plus a n n x n k plus 1 is b n. So, all of them are current iterate only. So, all of them will come to the left hand side. Now, let us look at the coefficient matrix. The coefficient matrix is a 1 1 A21 A22, the last row gives you AN1 AN2 ANN, that is nothing but L plus D. So, both of them are on the left hand side. So, I have L here, D on this side, I have got here x k plus 1 here, and I have got here only the upper triangular part has gone to the right hand side. So, minus u x k plus b. So, this is A11 A21 A22 AN1 AN2 ANN, therefore, this is L plus D on the left hand side. On the right hand side you have the contribution of the upper triangular part, that is minus u into x k plus b. Therefore, I can write this as x k plus 1 is minus L plus D or D plus L inverse of u x k plus D plus L inverse of b, which is our h x k plus c, where now the iteration matrix H is the iteration matrix is now given by minus D plus L inverse of u. So, this is our iteration matrix. Again the convergence properties of the Gauss-Seidel iteration method would depend on this iteration matrix minus D plus L inverse of u. Now, again for computational purposes I would still not prefer this, I would use the error format of the methods. So, just as we have done for the Jacobi, let us also do for the Gauss-Seidel also. Let us call this as the error format of this system of equations. I will do the same manipulation that we have done for the previous method. So, we shall write this as x k plus 1, I add and subtract x k again here, let us bring a minus sign here, I plus D plus L inverse of u x k plus D plus L inverse of b. I have added and subtracted x k from this particular set. So, x k here minus of x k and D plus L inverse of u. So, I retained it as it is. So, I have just added and subtracted x k. Again I will manipulate it in such a way, I take this D plus L inverse out on the left, then this will be D plus L. D plus L inverse gives us I. So, this is our I, and I have taken this from the left hand side. So, u will be left out, x k plus D plus L inverse of b. Now, again this is D plus L plus u, that is a again, D plus L inverse common. So, I will have here b minus a x k common here. Therefore, I can bring x k plus 1 minus x k, I bring it to the left hand side, this is minus D plus L inverse of b minus a x k. I have taken D plus L inverse common on the left. So, I have a b here and this is our a x k. Okay, we will put a positive sign here, we will put a positive sign here. Now, in the notation of the previous method, this will be simply V k is equal to D plus L inverse of R k. So, this is again the same residual vector and this is the error of approximation, or we can use it as D plus L V k is equal to R k. This we are very well versed about this one, this is nothing but the forward substitution, this is D plus L of V k. Therefore, this is a lower triangular matrix, therefore, this is nothing but our forward substitution. You can look also in the sense of this is the forward substitution method. Now, you can see the difference between the two methods, because it is so trivial, I mean discussion of this particular aspect of the error format. You can see that both of them would require evaluation of R k. B minus A x k is the residual vector, we need evaluation of residual vector in both the methods, and whereas in the Jacobi we are only having d inputs. So, we are only dividing by the one division for each equation, that is a11, a22, a33 and so on, one division per equation, whereas here you have got forward substitution and we know the count for the forward substitution here also. So, this gives you forward substitution and that is the direct replacement, but theoretically we can show that this method converges at least 2 times faster than the Jacobi iteration method. Now, before we analyze it, let us just take an example on this. So, I will take this as an example. One more just comment before we proceed on. In the case of the Gauss Seidel, we are replacing the right hand side vector whatever currently is available of the iterates. Therefore, we call it as the successively we are replacing the right hand sides as the solution vector current vector is available. So, it is called the successive displacement. In the previous case we have called it as the directly all of them are displaced on the right hand side. So, this is also called method of, there we call simultaneously all of them, here it is successively we are doing it, method of successive displacements. As and when it is available it is used, therefore, it is successively it is being used, displacements are used. Now, let me write an example. Solve the system of equations. Four x1 plus x2 plus x3 is 2 plus 2 x3 is equal to minus 6, x1 plus 2 x2 plus 3 x3 is minus 4. So, using the, let us use both of them using the Jacobi or simply Gauss Jacobi and Gauss Seidel methods. Let us also give the initial approximation. So, let us say assume the initial approximation as x0, the first iterate as 0.5 minus 0.5 minus 0.5. So, we are giving the initial solution vector also as 0.5 minus 0.5 and minus 0.5. Let us for the moment perform 3 iterations, and also let us obtain the iteration matrices. Now, let us write down the first the Gauss Jacobi method. Now, in the Gauss Jacobi we take the 2 variables to the right hand side and write this x1 k plus 1 is 1 upon 4 2 minus x2 k plus x3 k. x2 and x3 is taken to the right hand side, the current the previous iterate, and on the left hand side we have the current iterate. Second equation gives x2 k plus 1 is 1 upon 5 minus 6 minus x 1 k plus 2 x 3 k. So, x 1 and 2 x 3 are taken to the right hand side, these are the previous iterated values and the current iterate is here. From the third equation we will have x 3 k plus 1 is 1 upon 3 minus 4 minus x 1 of k plus twice x 2 of k. This is both x 1 and x 2 are taken to the right hand side and we will have this particular thing. Now, we are given the initial approximation as this. So, we are given x 1 of 0 is 0.5, we are given x 2 of 0 is minus 0.5, x 3 of 0 is minus 0.5. We are given these 3 values, initial values. So, I just have to substitute this and evaluate it. I will give the values that will be obtained over here. So, if I substitute them I would get here x 1 of 1, this is simply I am substituting the value of x 2 is minus 0.5, this is minus 0.5 and then simplify this one. I will give you the values of this. This is 0.75, x 2 of 1 is minus 1.1, x 3 of 1 is minus 1.1667. This is the completion of the first iteration by substituting the values of the previous iterated values in this set of equations. Now, this will be our new starting value. So, these values we will substitute on the right hand side, get our next iteration. So, the next iterated values are these: x 1 of 2 1.067, x 2 of 2 is minus 0.8833, x 3 of 2 is minus 0.8500. This completes the second iteration. We have got the values of x 1 of 2, x 2 of 2, x 3 of 2 using this set of values, and the third iteration gives x 1 of 3 is 0.933, x 2 of 3 is minus 0.733, x 3 of 3 is minus 1.00. The exact solution I may give, we can compare it. Exact solution is 1 minus 1 minus 1. So, this is the solution vector is 1 minus 1 minus 1. Now, I need the iteration matrix for this. So, we have written the iteration matrix for the, maybe I will take a different color, as minus D inverse of L plus U. Therefore, minus the diagonal part of is 4 5 3 is the diagonal. So, this will be 4 5 3, all right, let us put zeros here, and the remaining part is L plus U. L plus U will give you, oh yes, inverse, we will put inverse here, and then L plus U is the remaining part. So, we will have diagonal elements as zeros here, and the remaining part is 1 1 1 2 1 2, that is your 1 1 here, 1 and 2 here, 1 and 2 here. Now, the inverse of D would simply give us 1 by 4, 1 by 5, 1 by 3 here. So, this gives me 1 by 4 0 0 0 1 by 5 0 0 0 1 by 3, and we multiply this by 0 1 1 1 0 2 1 0 this. So, I can just multiply it, this it gives me 0, 1 by 4, 1 by 4, that is this row and these 3 columns. Then the second one 1 by 5, 0, 2 by 5, and the third row would give us 1 by 3, 2 by 3, 0. So, this is the iteration matrix for our Gauss-Jacobi method. Now, this we are going to use it later on to study the convergence properties of the Gauss-Jacobi and also to obtain what is the rate of convergence, how fast it is converging. Now, let us take the Gauss-Seidel. So, let us do Gauss-Seidel. Now, whatever we have written here will now be rewritten, except that here we will have x 1 k plus 1 and here both of them will be at k plus 1th iterate. So, let us rewrite this system. So, this will be x 1 of k plus 1, the first equation remains as it is 1 by 4 2 minus x 2 k plus x 3 k, yes, then x 2 k plus 1 is equal to 1 by 5 minus 6 minus x 1 of k plus 1 the current iterate, 2 times the x 3 of k the previous iterate, then x 3 k plus 1 is equal to 1 by 3 minus 4 minus x 1 k plus 1 plus 2 times x 2 k plus 1. So, here we have got all of them at the current iterate. Now, again we start with the iteration, starting the initial value is given to us again as x 1 of 0 is 0.5, x 2 of 0 is given as minus 0.5 and x 3 of 0 is equal to minus 0.5. Then I substitute it here, the first value would be the same as the previous because the first iteration is the same. Now, you can see that the current value of x 1 k x 1 of 1 has changed to 0.75. Therefore, the second solution is going to change substantially because in place of 0.5 which was the previous iterate, now we are using current iterate as 0.75 over here. Now, and this value comes out to be x 2 of 1 is minus 1.15 and similarly x 3 of 1. Now, when I solving for x 3 of 1, I have got x 1 of 1 available to me, x 2 of 1 is also available to me. So, both these values that are now will be used on the right hand side and this value comes out to be minus 8167. So, I would give you the remaining iterates also. What I would get here, x 1 of 2 is equal to 0.9917, x 2 of 2 is minus 0.717, x 3 of 2 is 9414, wherein I have used in the first step the previous iterated values and in the next step I have used this contribution here, and in the third value we are using both these values, the current iterates here and then obtaining this value, and the third iteration gives out values this 1.0053, x 2 0.3 minus 0.213, x 3 is minus 0.9876. Now, this is the solution value that we obtained after the third iteration. Now, it would be interesting for us to compare this value with what we had obtained in the Gauss-Jacobi value. If you look at this, the Gauss-Jacobi values, this was 0.9333, exact solution was 1, and here we got 1.0053. This value is very close. This is 0213, 0733, 9816, and this is minus 1.1. Now you can see that even for the simple problem of a 3 by 3 system, it is so clearly visible that the Gauss-Seidel is much faster compared to the Gauss-Jacobi scheme. Now yes.
But still we are using the latest value for x1 and x2 in calculating s3.
Yes.
So but the error is the most in the x3 terms.
Error will be, yes. Now it's after few iterations, initially it is trying to adjust its values. Now as the number of iterations, so suppose you take 1000 equations, when once you come to the x 1000 value, after few iterations you will see that this is converting very, very fast. It actually takes time for the iterations to adjust its values, and afterward the convergence will be very fast. Now let us write down the iteration matrix for the Gauss-Seidel also. So let us write down the iteration matrix. Now the iteration matrix, let us give a suffix to it. We will put GS, Gauss-Seidel minus D plus L inverse of U. So this is our minus D plus L inverse of U, and that is equal to, let me just go back here and then write from here, our D plus L will be 4, 1, 5, 1, 2, 3. So that will be the D plus L part. That means I have here this is 4, 0, 0, 1, 5, 2, 1, 2, 3 inverse. That is our D plus L is 4, 1, 5, 1, 2, 3. So this is our D plus L inverse of this, and U is the upper triangular part. So this strictly upper triangular. So let us put them 0, 0, these are zeros, 1, 1 and 2, 1, 1 and 2. This is your 1, 1 and 2. So this is your U part. Now D plus L is always lower triangular. Therefore I can obtain its inverse by using the property that L inverse is equal to I. So I can use that this is a lower triangular, this is a lower triangular matrix. So I would in general use this, we are using that notation, some let us call it as L star. So I can use this property that L star is equal to I, and forward substitution. I am talking of a big matrix. For small matrix we can do it directly, but for when it is a system is very large, I would use this notation and get this one. So the I can immediately write down, find the value of the determinant here, that is equal to 60. So we will have here minus 1 upon 60. I can write its cofactors. This is for this element, this is 15, for this element this is 12, for this element this is 20, and the inverse of a lower triangular matrix is lower triangular. So I can put those zeros over there straight away. Now I can take the cofactor of this, remove this row column, I will have a 3 here. So I will have a minus 3 here. I take cofactor of this corner element, that is 2 minus 5, that is minus 3. So it stays on there. The cofactor this element is 8, therefore I will have a minus 8. And this is being multiplied by 0, 1, 1, 0, 0, 2, 0, 0, 0. So let us multiply it out, 1 upon 60. Now you can see that the first column, because these are all zeros, therefore this is also 0. So this is always going to be 0. These are all zeros. So the first any row you multiply by this is all going to be 0. This is 15 and third row 15. The first row third column gives me 15. Multiply with this, I would get here minus 3, and this is minus 3 plus 24. So, I will have here 21. Third row, second column gives again minus 3, and this into this gives you minus 3, minus 16. So, I will get here minus 19. Now, interestingly, the Gauss-Seidel methods will have the iteration matrix as zeros in the first column. It is trivial because we are taking only u is the one that is being multiplied here, and u has got zeros in the first column always. Therefore, the product will always contain zeros in the first column for the iteration matrix of the Gauss-Seidel. This is of course an advantage for us. We will see as we analyze the method for the finding the convergence rate. This will be of something little use for us because it will reduce the amount of work. So, this is a fundamental property of the Gauss-Seidel, that the first column of this will be the same thing. I think we will still stop for this today.